All right. Thanks everyone for coming to the second day. So our first speaker is Christos Papadimitriou, who's a professor of computer science at Columbia. And I'll remind everyone, we decided to do brief introductions, which is good because otherwise to list all his awards would take most of his talk. But Christos is one of the founders of Econ CS in general and has been a leader in the area for quite some time and has a lot of work prior to that in complexity theory and all over theoretical computer science generally. And then we're very excited to have him speak with us today. Thank you.
Many thanks, Matt. And thanks for inviting me. I'm very happy to be here. So, as you know, we're here to honor and celebrate a remarkable mathematician and computer scientist. If you, as some of us might have done, have looked at his opus recently, I mean, it's hard not to be impressed and inspired by the breadth, of the work, because Mark has essentially gone throughout the whole world of science and picked some of the most fundamental and hard problems to work on. And we're lucky that most of them were in the field, in the intersection between computer science and mathematics. But he has also worked on dynamical systems, the subject of my talk. And 7 years ago, when I was starting to work on dynamical systems, I read his papers and then I met with him for an hour. And that was a remarkable, we had a remarkable conversation. So, so I'm here to brag to him what I have done since then. Okay. Yeah, so, all right, cool. I want to start by pointing out that my title is redundant because essentially, we only compute with dynamical systems, right? I mean, if you think about it, because the chip is a dynamical system. God knows that the quantum computer is a dynamical system. And of course, where the most interesting computation happens, it's also a dynamical system. I don't know the world's most fascinating dynamical system. And when many of these interact, that's called markets or game theory, each with its own goals and incentives. Then dynamical systems become very interesting and complex. And these are the dynamical systems I'm going to talk about today in brains and games. Okay, and I'm going to try to touch on some of the most important questions in these fields. What is the true meaning of the game? And how does the brain make language? Okay, so these will be my two topics, right? Very different. Okay, so if you are, I'm going to start with game theory. So if you are lost there, hang on. Okay, cool. What is the meaning of the game used to have a very simple answer. Okay, a very widely accepted answer. It is the Nash equilibrium. All right, it is. It's an incredibly attractive concept. It is very elegant. It catches a lot of what the game theory is about. Social interaction between individuals. There is always a situation in which nobody has any incentives to deviate. Okay, that's incredible. Okay, that's an amazing result. Also, it's a very inspiring and influential result because it inspired Arrow and Debré to change the face of economics. Okay, so how do I know? Kenneth Arrow told me. Okay, that this is where they drew their inspiration for essentially starting welfare economics. And it's also a powerful conceptual tool for economics research in the sense that Nash's theorem is a license for any economist when they design something or they contemplate something, a situation, an institute, a market, to sit back and think, let's see what happens at equilibrium, okay? And they know that there's going to be an equilibrium. Roger Myerson, 26 years ago, said the Nash equilibrium lies at the foundations of modern economic thought, okay? Except that the last 30 years, computer scientists have been involved with the Nash equilibrium and game theory. And from this interaction became clear that the Nash equilibrium is not computational, okay, in several ways. the most obvious one is that it's intractable. Okay, that there is, if the world of complexity is what we think it is, there is no way to find it. Okay, I mean, many computer scientists have doubts about intractability. I mean, because in practice, is it important? Does it tell you anything in practice? Okay, I mean, they're right. I mean, we all know people who make a honest living by solving intractable problems. Okay, but the point is, I mean, even if it's irrelevant in practice, in theory, okay, I told you that the Nash equilibrium is a theoretical instrument. Okay, not a practical instrument. Good, and also. By the way, I don't know the story, but when Nash proved his theorem, John von Neumann looked into his heart to find the most kind and encouraging words to tell a brilliant young mathematician who just proved an amazing theorem. And this is what he came up with, okay? So, and in fact, the man was right, okay? When I say the man for von Neumann, I mean the man, okay? So he was right. The source of the troubles of the Nash equilibrium come from the fact that from its genericity, okay, that it is a generic fixed point. And this is what we call Pipad complete these days, okay? And so, also, perhaps more damningly, the Nash equilibrium is not unique. And and this leads to, to the equilibrium selection problem, okay? And two great mathematicians and game theorists, Harsanyi and Zelden, 30 years, 50 years ago, decided to put an end to this and they wrote a book about a principled way of selecting one of the many equilibria that the game may have. And they got terribly stuck, and then they did something remarkable. They turned around and they published the terrible way in which they were stuck. Okay, and years later, it became apparent. I mean, we wrote a paper about it, that the problem they were setting up is p-space complete. In other words, a million times harder than finding a Nash equilibrium itself. Now, if you explain this to an economist, they will tell you, yeah, but the players eventually will get there. Okay, and I mean, as a complexity theorist, I don't believe it, but still, all known learning dynamics, which were invented by game theorists and economists expressly for the purpose of finding behaviors that lead you to the Nash equilibrium, fail to get you to the Nash equilibrium for some games. Okay, is this clear? I mean, and so this must be an important problem. Assign to each game a dynamic that always converges to the Nash equilibrium and stays there. All right. So here's the news. There are games for which no such dynamics exist. Okay, that it's a resulting algebraic topology essentially, right? I mean, basically it's an impossibility. You cannot have a dynamic that does this. A discrete time or continuous time. Okay, even to converge to approximate Nash equilibrium. Okay, even for this there is no dynamic. So, I mean, this sounds to the untrained ear like a weakness of the dynamics approach. Okay, but I believe that it is the final blow to the Nash equilibrium. Okay, and I'm proposing to redefine the meaning of the game as the way in which the game dynamic changes the players. Okay, and I'll be more specific. Let us fix the most natural dynamic, the replicator dynamic, which is gradient descent on utility. Okay, it's like the greedy algorithm. It's also the small step limit of a famous algorithm called the multiplicative weights update algorithm. All right, so, importantly for economists, if you change the baseline or you change the currency, it does not change. It's essentially invariant. All right, I mean, also otherwise economists would not go with it. By the way, there is one criticism of this dynamic as a natural dynamic. And the fact is that it is deterministic, okay? And in any deterministic dynamic, the other players have an incentive to take advantage of you if they know what you are going to do, right? I mean, also, and in fact, Mark was one of the first people who studied this phenomenon and, trying to get to exploit a player who plays no regret algorithm like this, okay? And there has been a lot of literature since his paper. And the consensus is that, yeah, you can do something, but in general, not much, okay? So in any event, that's my proposal. Let's focus on the replicator dynamic. And here is the definition of the meaning of the game. The meaning of the game is a mapping that maps a prior on the player's strategy to the limit distribution of the attractors of the replicator in G. Okay, so if these people play long term this game, how will this change them? Okay, but how can we compute the attractors of a game? Okay, first of all, is there a finite number of them? We don't know. And are they computable? There are simple games with infinite many attractors. Even replicator dynamic is known to have chaotic attractors, and the computability is also known to be bad for dynamical systems. So, but there is a combinatorial structure surrogate of the replicator, and that's better response dynamics. If you have a game like this, the column player wants to move this way. Oops, yeah, it went a little too far, okay? And the row player wants to do this, okay? Because 1 is better than -1, okay? So this is sort of, the pure strategy dynamics. And it's the preference graph, okay? So, you get, and it also has an associated Markov chain because you can put numbers, which is the difference, and then normalize, and you get a Markov chain, okay? And you must include also tie edges with infinitesimal probability. Okay, that's what makes this problem hard. This Markov chain is the limit of the replicator dynamics when you are at the skeleton of the polytope. When you start, let's say, from a pure strategy. All right, and the attractors of these dynamics are easy to compute. They're the sync strongly connected components of the graph of the Markov chain. And in fact, these have been studied for the last 20 years by computer scientists in different contexts for games. Right? So, I mean, if you want to compromise that much, you are in very well-charted territory, right? But is there a relationship between the sync equilibrium and the attractors of the game? Okay, that had been a big question ever since I started 7 years ago to think about this problem. And recently there was an amazing theorem, okay? Topological proof. There are, in many to one correspondence, each attractor contains one or more sync equilibrium. Okay, so they are not unrelated. Okay, they're quite related. And in fact, immediately you conclude, yes, there are finitely many attractors, right? Okay, so it suddenly becomes a nice problem. And of course, with Pilura's who conjectured back in 2019, and Bigger and Shames reiterated this conjecture, that the correspondence is 1-to-1, okay? If this is true, we are done. We are done in a huge way, okay? So, we have an easy way to compute, but I mean, we have to prove this theorem, okay, to prove this conjecture. It's not true, okay? We just proved with Oliver Bigger, who has since changed teams, and he's my PhD student at Columbia, that it's false, okay? That sync equilibria can leak flow, okay? In other words, that the dynamics can leave in certain case, under very special circumstances, the sync equilibria, a node. And therefore, this sync equilibrium is no longer an attractor, okay? I mean, also it's part of a larger attractor. Good. And at the same time, we came up with two positive results. Positive in the sense that the attractor characterization problem, which becomes complicated by that theorem, we make progress on it. First of all, the conjecture holds for something we call the pseudo-convex games, which is a new class that generalizes the both classes that for which we knew it holds, okay? The zero sum and potential. And second, if the sync equilibrium is a cycle, then there can be no leaks, right? And so then you know that's an attractor. And that's important for some games like the Shapley game, okay, and the Jordan game, which have strange cycles as attractors. And the big open problem here, of course, is characterize and compute the attractors of the replicator in any game. And in the meantime, a recent result that we proved with my students at Princeton, at Columbia, what did I say, and George Pillars, the mapping from a prior distribution on pure strategy profiles. Okay, if your prior is on pure strategies, okay, has pure support to the limit distribution of the Markov chain over the sync equilibria, can be computed in almost linear time. That's a difficult theorem because that's a difficult algorithm, sophisticated algorithm because of the epsilon edges. And this allows us to approximate the mapping mu sub g of the noisy replication for very large games. I mean, we can on a laptop we can compute this mapping mu sub g for we can approximate it for games with tens of thousands of pure strategies. Okay, so to summarize, the Nash equilibrium is plagued with the computational shortcomings. Game dynamics provide a powerful new way of redefining the meaning of the game. It suggests a novel solution concept that seems largely free of computational downsides, but it's of course it's approximate. It's notice that the sync equilibrium, in some sense, is an alternative. Okay. The only solution concept that no game theorist ever dreamed to object to is the pure Nash equilibrium. Unfortunately, it's not universal. Nash had the ingenious idea to generalize it to mixed Nash equilibrium, to mix Nash equilibrium and prove that it is universal. If you generalize it in a different direction, okay, in the sync components, which is a generalization because sort of if the sync component is a singleton, then it is a pure Nash equilibrium, right? I mean, so if you in a different direction, you get a different solution concept. The approximate meaning of the game can be computed very fast for very large games, and there seems to be a fascinating, I believe, profound mathematical problem: compute the attractors of a game. Okay, given a game, compute its attractors in polynomial time. Okay, the four theorems: impossibility, the sync equilibria are connected with attractors, but not as closely as we thought. And if we compromise, then we can do wonders computationally. Good. To the younger people in the audience, if you don't know what this is, find out, because it will help you understand your parents and their humor. Okay, okay. So how does the brain make language, right? So this is a 150-year-old question. I mean, and there are, these are the two latest amazing books by Kemmerer and Friedrich. Completely different viewpoints for this. Noam Chomsky made this question famous, Wernicke and so on. I mean, so what is happening now is beyond belief. Okay, I am creating vibrations in our common medium, and these vibrations become trees in your brain. Okay, that's not normal. Okay, this is no other brain has been able to do this. And if I'm extremely lucky, you will never forget these trees. Okay, how on earth can this happen? Okay, it has been obsessing a lot of people in many fields: linguistics, neuroscience, cognitive science, cognitive linguistics. Has created many fields: neurolinguistics, cognitive linguistics, and we are not close to answering it. Okay, and there seems to be, the way people talk about this amazing problem, and everybody talks about this problem, gives me the impression that that they have a tacit hypothesis, and that's that language is enabled by a set of novel neural features at the molecular, circuit, or cellular level, or systems, which are unique to the human brain. In other words, that we must have a unique characteristic that enabled us to do language. Okay, and in fact, for the longest time in the 90s, this gene here, FOXP2, was called the language gene. Okay, for almost a whole decade, and then you discover that it does something completely different, which happens to also affect language ability, speaking ability. Okay, so that was one sort of dead end. So recently, we discovered that there are human cells that have characteristics of their dendrites, of the dendritic computation, that are much more complex and advanced than any other dendritic cell, neural cells we have studied. And immediately people said, that's language. That must be language. Okay, so this seems to be a very, very well accepted, very well sort of it's implicit, but it's tacit. But I believe that a lot of people think about it. And in science, when you have any hypothesis, okay, you better have the null hypothesis. Okay, and the null hypothesis says that a language system can be built on top of the mammalian brain from simple components and a few basic, widely accepted neuroscience principles. Right? That's a null hypothesis. And I'm going to talk about the null hypothesis. Is this clear? Do I make sense? Okay. By the way, I want to build a language system, okay? And this is, according to Richard Feynman's enigmatic last pronouncement, what I cannot create, I do not understand, okay? And the contrapositive the converse is very interesting. Good. So, but there's a problem. Nobody knows a few basic and widely accepted neuroscience principles. Okay, really what had happened that the last let's say 50 years, neuroscience has advanced faster than any other field except for AI the last decade. Okay, literally has advanced faster than any other field I know. And we learn every year so many things about the brain that we are lost in the forest. Okay, and it's not my impression as a newcomer to neuroscience. I've been working on this for 10 years only. But very seasoned researchers say this. For example, this may be the greatest living neuroscientist, my colleague at Columbia, Richard Axel, Nobel 2004. And what he said is this: we don't have a logic for the transformation of neural activity into thought. And I view discerning this logic as the most important future direction of neuroscience. Now, this is amazing. Axel is the world's most dedicated empiricist, okay? And uses logic. Logic means that it is our job to solve the greatest problem in neuroscience. Think about it. Okay, logic means a theoretical tool that is ultimately computational. All right. Okay, so the challenge is take this book. I teach a class on neuroscience, and this is my office during office hours. So my door. This is genuine. I didn't make it up. My doorstop doesn't work, and you can see it's broken. And I use this book as a doorstop. Okay, and this book is called Principles of Neural Science, and every 4 years it's being reprinted. And every time it's reprinted, it's 200 pages longer, okay? Which is absurd for a book whose name is Principles, okay? Because principles should get fewer and fewer and fewer and fewer. When the Greeks decided to find the principles of geometry, they ended up with 5 lines, count them, 5 lines, right? So can we articulate a few basic principles that are essentially enough, okay? Notice, of course, that now we are faced with 2 problems: how the brain makes language and how does the brain work, okay? So and I propose to solve them both in the same fell swoop. Okay, I'm going to introduce NEMO, okay, for neural model. It is the world's simplest model of the brain in the sense that if you omit any of these bullets, either it becomes more complicated for no reason, or it does nothing, okay? Cannot learn. Okay, it's you can prove that no learning can happen. Okay, so excitatory neurons. Okay, in brain areas. Okay, they're divided in brain areas. That's very important. Random synapses weight initialized randomly. Okay, they're GMP, Erdős-Rényi directed graphs. Okay, in every. Also, Okay, random synapses within each area. Certain pairs of areas are connected via Erdős-Rényi bipartite graphs, directed bipartite graphs, okay? Inhibition, that's a very important part, okay? And again, without it, you can't do anything. So every brain area we know, along with excitatory neurons who do the heavy lifting, it has a minority, I don't know, 20, 30% of inhibitory neurons. And their job, they're scattered around them, and their job is to selectively silence the vast majority of the neurons that want to fire, okay? Because without that, you get seizures, you get strokes, okay? So thank God for inhibitory neurons. But the point is that at any moment, in every area, only a small fraction of the neurons can fire, okay? Let's say out of the 1 million neurons, N is 1 million typically in our experiments. Only 1,000 can fire, okay? So that's what this, so it's a K winners takes all. Basically, it says the following, that in order to compute which neurons will fire, in every neuron, in every area, we do the following. We compute all the synaptic inputs it has collected from the previous step, from its area and from other areas. And then we select among these neurons the K, the 1,000, with the highest such synaptic input, and this fire. And you go on, okay? That defines a system. I say if the whole area, unless the whole area is inhibited, there is also inhibition mechanism. I'm not going to bother with it. It's a simple biologically plausible inhibition mechanism that sometimes, depending on what fired, may inhibit an area. And there is Hebbian plasticity. Without this, of course, you cannot learn. Hebbian plasticity is the simplest form of plasticity. By now, there are like 500 different kinds of plasticity that we have discovered. But Hebbian plasticity is the simplest one. If neuron I fires, and neuron J fires one step later and there is a synapse from I to J, then the strength of this synapse is increased by 5%, let's say, by beta. And that's it. No, that's the whole dynamical system. It's completely defined from what I have told you. The state is the neurons that spike, synaptic weights, and inhibited areas. And the next step function is fully defined and very important. It has an emergent behavior. Okay, if you let it go by itself, how does it start? You have some areas that are stimulus areas, and there you have they fire selected inputs fire. Okay, you you have some of them you have sets of 1,000 neurons that fire, representing things that the animal heard or saw. Okay, and if you let it work like this for a while, in the end, representations of these stimuli are going to emerge in various, or combinations of the stimuli are going to emerge in various areas. Okay, this is you can prove it actually that this will happen, and representations of symbols by strongly interconnected sets of K neurons in an area. I mean, those of you who remember the AI debates of all days, there was a symbolic versus non-symbolic AI. I mean, and the human brain was all supposed to be both sub-symbolic and symbolic, and this is where symbols start. Okay, this is the genesis of symbols, and they comprise the attractors of this dynamical system. By the way, the dynamical system is deterministic but random because it starts with a random graph. Okay, so all of our theorems have to be with high probability theorems, right? Okay, good. By the way, okay, there's no backpropagation here, right? So if you are thinking you are doing language, how do you compare with LLMs? That's not my business. Okay. Good. NEMO is very efficient. I'm not going to tell you this, but basically, even though it would be impossible to do to simulate NEMO for what we needed without tricks, we have found tricks, both programming and mathematical. For example, we do a lazy evaluation. We only look at neurons that have fired in the past, and new neurons are generated. Fresh neurons are generated by sampling from the tail of some distribution. Okay, so we do tricks like that, and then the result is that we can simulate up to 20 brain seconds on a laptop. Okay, and these are the experiments I'm going to show you. Going back to language, can we implement in NEMO a biologically plausible language system? This is what I'm going to present you. This is the result I'm going to tell you about. The hardware is a tabula rasa, in other words, no knowledge, zero knowledge of language, of course, yeah, of a dozen or so brain areas, fibers, and populations of LRIs. That's the inhibitory neurons that do the inhibition. Input is a modest number of grounded sentences in any natural language. Okay, both modest and grounded are key, and I'll have to define them. Okay, modest means not the ChatGPT way, okay, but the human way, right? I mean, so, and incidentally, Chomsky has been insisting on modest, but nobody has defined modest. Okay, computer scientists had to start thinking about the subject to define modest. Okay, so and I'll define modest soon. The output should be a mature language system able to comprehend and generate sentences in the same language. Okay. Okay. We choose a natural language as a number n of tangible nouns and action verbs. Okay, n right now is like 40. Okay. Transitive like cat, box, chase, eat, toy, dad, grab. Okay. There is no words like mystery, no verbs like negotiate. Okay, I mean, they have to be tangible and action. Okay, and that's how babies start. We choose order of n. That's what modest means. Okay, a small multiple of n sentences. The constant doesn't have to be more than a dozen in our experiments. Using these words like the dog runs, sis grabbed the toy. Okay, if we have 40, we probably generate 1,000 sentences with these 40 words. We input the sentences in a grounded way. Okay, what is a grounded way? By the way, we have a convention. How do we input? When you say the dog runs, we press a button. The dog runs. Okay. In other words, we assume that phonology has been solved. Okay. We do, it's a very interesting problem. We don't want to deal with it. Okay. So basically, we assume the assumption is that the baby has learned to recognize the word dog and articulate it, but has no idea what it is. Okay, I mean, so these are assumptions. And what does grounding mean? The dog runs grounded, okay? What we display is in semantic areas, which are basically areas in our temporal lobe. The generic dog, okay? Everybody, by that time, the baby has an image in the inferotemporal cortex of a generic dog, okay? Can recognize dogs. The mirror cells for running, okay? We all, we all have mirror cells for even if when we don't run, if we see people running, the mirror cells work. And then maybe there is an auditory stimulus that comes with it. Maybe there is an affective stimulus. We love dogs, we fear dogs, okay? And these are displayed, okay? This is what it means for the dog runs to be grounded, okay? These are displayed at the same time, all right? In other words, but not in any order, okay? They are displayed at the same time. Is this clear? So that's what grounding is. And then what we want to create noun representations. We assume that there is a phonetic area where the word dog is rooted. Okay, I mean, there we know how to articulate it, how to recognize it, later how to write it. Okay, how to read it, and neuroscientists believe, neurolinguists believe that such an area exists. Then there is a lexical area for nouns. Neuroscientists believe that there are both separate noun and verb lexical area. There is a symbol dog, okay? There is a representation, an assembly representation of a simple dog, which is created, okay? This is given, and this is given, okay? The device starts with this, okay? But this has to be created. It has to be created in the right area. And it's connected with the semantic areas. And because this is a noun, it is connected primarily, most strongest of all, with the vision, okay, with the image of the dog, because that's a noun. That's a tangible noun. Verbs, the same thing, okay? That's for crawl, okay? I mean, except that now it's the motor cortex that has the primary. That is strongest connected by strongest synapses with the representation, with the symbol. This is lex for verbs, all right? All this, by the way, I have been telling you, is agreement with current opinion, wherever consensus exists. Okay, I mean, so some things we had to take some initiatives. So that's I described to you our experiment, the input. What's test one? Has the device learned the syntactic role and meaning of the words? After the presentation, we check that robust representation of each word. In other words, we probe dog, and we make sure that there is an assembly in the noun area. It is strongly connected with the image of the dog and the word for dog. And there is no such assembly in the verb area. In other words, the baby has understood that dog is a noun. And the opposite for verbs. Everybody following? This is highly non-trivial. Here is why. Consider dogs run in English and Irish. If the language is English, dogs is the noun. If the language is Irish, dogs is the verb. You see, because in Irish, verb comes first. So the baby has no way of knowing if this is English or Irish. So must figure it out. Okay, so this is done by implicit statistical learning. Okay, this we had no right to expect that this would happen. We cannot prove that it happens. That was our lucky break. Okay, it does happen very robustly. And there's a second test, the last test. Can it generate? We present the center morpho system a scene that was never seen before. For example, a dog chasing a cat. And the device should output the dog chases the cat. Okay, that's the test. And it does, robustly. But why not the cat chases the dog? Okay, if we presented the cat, a dog, and the verb chase. Okay, and the reason is, how are the roles of the two nouns determined? The reason is that primates cannot survive without having a device when they see something to know who is doing what to whom and who is watching. Okay, I mean, other than that, sort of, if a primate cannot do that, will not do well. Okay, and there is a mechanism, and we have been tracing it in the temporoparietal junction that does exactly this. When it sees a scene, it analyzes it into agent, action, and patient. Okay, and we assume that this device is in place. As I told you, I don't want to invent the wheel. I want to build a language system on something that primates have. Okay. This is the device, our device. I believe it's more than a dozen areas. A total of maybe 20 million neurons, 1 trillion of synapses, and I'll show you. Oh, that's probably our most surprising result. Okay, you know that languages have different word orders. Okay, in the only 3 languages that matter now, which is English, French, and Greek, the word order is subject, verb, object. Right? Word orders are different, okay, vary a lot in frequency. SVO, our word order, is 42%, is not a champ. S order, subject order verb, object verb is the Latin, the Latin word order, okay, is the champion. And the others are much less, okay? Verb first is only 10%, and object first almost doesn't exist, okay? So this is an interesting experiment. Incidentally, speaking of languages, I want to pay tribute to a language that was once spoken in my hometown, the island of Manhattan, and now it's only spoken by about 100 people who live in the town of Muncie, southern Ontario. The language is Lenape. Okay. Every 2 weeks, a language disappears. There are 10,000 languages right now. Okay. So here is our result. The 2 rarest word orders are the ones that require the most input sentences to be learned. Okay. The 3 rarest word orders require to be learned that the clear majority of input sentences include transitive verbs. In other words, if you only teach them, if you teach them with predominantly transitive verbs, the baby will not learn the word order. Okay, and I think, yeah. Of course, yes. So there are many. Okay, I mean, this is absolutely, yes. Je le sais. I understand. This happens in many. The pronoun thing happens in many languages. In Greek also. We have not. I mean, one of our open problems is to go and look at, for example, okay. When you get to adjectives, okay, in English it's adjective first. In French, unless it's beau, bon, mal, it's yeah. So there are many wrinkles that we want, and I'll show you. Actually, I'll tell you. I'll point to this. Okay, but you are absolutely right. So So, I mean, language is unending. Okay. In any event, this is consistent with the two hypotheses that the word order of languages evolved, with fitness being the ease of learning the word order, which makes perfect sense to me, and a lot of people believe it. And a lot of research on word orders is based on this assumption. And second, that the human word order learning system is similar to NEMO's. Okay, if it's the human, so in other words, okay. Good. Next steps: scale to 200 words, which is what 2 years old know. Ultimately, 10,000 words. Abstract words. We are working on this. The 200 words were close. Social language. Social use of language, which is an very important subject. I mean, so what we have thought is to have NEMO be adapted by an LLM, okay, and teach it how to interact. Many things, syntax beyond word order. The third one is exactly what you are saying. I mean, ambiguity, grammaticality. How do I know that the sentence is correct and it's not? Sentence embedding and recursion. I mean, how do you do next word prediction? Metaphor, reasoning, theory of mind, and so on. All these are things that are open-ended. Enhancements of NEMO may be needed. Okay. So this is the team who did the top row, and Kelly is dynamics for games, and Santos and Max Dabadja and Mitropolsky. Santos is my brother in arms in this. We have been working on this for 15 years now. Max Dabadja and Dan Mitropolsky are PhD students, now postdocs. And thank you very much.